All right, so we left off Friday talking about linear regression. So we'll keep going through that. We'll kind of pick up where we left off using the same data set. We'll then kind of maybe dive into some additional issues here today. So where are we at? We were working with this GPA omitted variable kind of data sheet or worksheet. We had a regression run. I'll kind of go back through how we did that final one just to kind of see it again. So hopefully at this point, we have that data analysis added in. If not, we go to options, add-ins, manage the add-ins, make sure the analysis tool pack is there. On a Mac, like I said, if you go through the tools bar and you see add-ins and you make sure that this is checked, right? So once that's checked, we can go to this data tab, go to data analysis, scroll down to regression, hit OK. So our Y variable, we were trying to predict GPAs, right? So we select college GPA and select the entire column. Just Control Shift or Command Shift on a Mac and hit the down arrow. Then for our X variables, we're just going to throw the kitchen sink in it. So I'm going to include everything over here on the right-hand side. Okay. So Control Shift, hit the down arrow. I selected my label, so I make sure that box is selected. I hit OK. And I get my output. Right? So we kind of went through that last class, if I recall. Right? We looked at the effect of being a student athlete on GPAs. We then added in just the SAT measure as an additional control variable. And then we said, what if we added in everything? Okay. So is this looking familiar? We're up to speed at this point. Okay. So we're going to zoom in here so I can see this a little bit better. But using this output, right, we can pick up a few things. So this R squared, right, that's going to tell us the percent of the variation in this original Y variable that we're explaining with all those variables we include on the right-hand side. So we're doing a decent job, right? We would like this to be really close to 1, but at this point, we're explaining about 30% of the variation in GPA, okay? We then have all these variables we could start to kind of interpret the coefficients on them. So for instance, on SAT, we said for every 1 point increase in the SAT score, the predicted GPA would actually go down. However, this is going to be a little bit weird because something I'm not going to expect you to know how to do is I included a squared term. So this is going to pick up that there's some quadratic relationship with SAT scores. So this might look not intuitive, right? But it's because the total effect of a 1 point increase in SAT, right? If SAT goes up by 1 here, it's going to impact this variable as well. Right? So you can kind of imagine if I had written out my regression equation, I'll kind of shorthand it here, but so GPA will have some intercept, I'll have SAT, and let's for now say I include this SAT squared, athlete, all these other variables, right? Well, I can come up with the kind of total effect of a 1 point increase in SAT score. But notice if SAT goes up by 1 here, GPA would go up by beta 1. But also if it goes up here, right, a 1 point increase here is going to impact the coefficient as well. And what ends up being true, right, if we take a kind of derivative of this function in respect to what's changing. So, right, the change in GPA from a change in SAT, we're going to get this guy here. Now, I'm not going to expect you to know how to do that. I'm just mentioning it because it's there in the output. And past this course, you could pick up these nonlinear relationships, right? So maybe it looks, I think actually what data looks like is something like this, so that the line of best fit would look something like that. Okay. Now, kind of punting on that, right? I'm not going to expect you to know how to understand these nonlinear relationships. We do need to understand that we can make predictions using this model. Okay. So to avoid the SAT squared, I'm going to rerun this and just run it without that. I just wanted to make you aware that that is a possibility. And since it was in the data set, well, let's just run it now and force that relationship to be linear, right? So I only include up to the variables right before SAT score squared. We'll zoom in. Okay. So now if I'm looking here, it looks a little bit more like we would expect. A 1-point increase in my SAT score would predict that my GPAs, or my Y variable, goes up by 0.001. Okay. Now that may seem small, but that's the effect of one more point on the SAT. That shouldn't be that much more predictive. What if someone scored 100 points higher? Well, if I know the effect of 1 point, we said the effect of 100 I could just get by multiplying this by 100. Right? So I can scale this up to whatever level I want. Now, if I think about somebody going from a 1100 to a 1200 on the SAT, that would predict their GPAs are about 0.16 higher. Right? Not the largest effect, but right, we got a Y variable that only goes from 0 to 4. Okay. So with that idea in mind, once we obtain all the values, for these coefficients, I could then, all these would be numbers, I could take a hypothetical person, plug their values in for the X variables, and come up with what their predicted GPA would be. So for instance, if I had like a really simple linear regression, and let's say, I don't know, I run this regression and I get, I don't know, 1.2 plus 0.002 times SAT, right? Let's say I just run this really simple linear regression. I could come up with predictions about the GPA by just plugging in different values for SAT scores, right? Somebody who gets 1,000, right? Well, this would be what? Move the decimal point 3 places. So 1.2 plus 0.002 times 1,000 be 1.4, right? And that's kind of the idea of how I would make these predictions. So it's more complicated because I have more variables, but this is generally how I would say to go about making a prediction for a hypothetical person. So we'll call this hypothetical person, right? So let's say this person got a 1200 on the SAT. They were not a student athlete. They scored a 0.7 on this verbal math test, which I believe ranges from 0 to 1. It kind of represents the proportion of questions they got correct. Their high school rank was maybe they were 15th. Let's say they were female. They were not white or black, so another minority group. They've currently taken up to 46 total credit hours. And this high school size variable was a weird one. I think it's in the thousands, if I remember correct. So like it's in the hundreds. So I think like 9.4 would be 940. So we'll just choose something that's kind of within this range. So we'll go 4.00 just to keep it easy. So let's say their high school size, like I said, I think this represents 400 students. Okay. So I've got this hypothetical person. How could I come up with their predicted GPA? Well, probably the easiest way to do this would be just take each coefficient, multiply by the X value for this person. Now, for the very first row here, we've got the intercept. Well, when we're writing out this equation, right, the intercept isn't multiplied by anything. It's always added in to our prediction. Okay. So if I'm doing this in Excel just to save myself some work, I'm just going to put a 1 in here, and that way the intercept always gets multiplied by 1 and added in, right? So nothing crazy there. So I then go through and take the X value for this hypothetical person, multiply it by that variable's coefficient, okay? I'm then going to do that for every single variable. Now, essentially what I have here are all the combinations of the coefficient multiplied by whatever that hypothetical person's X value is. Every coefficient multiplied by that hypothetical X value for this person, okay? So the next step is I just need to add them all up, and that should give me my predicted GPA. So how can I do that in Excel? I'm just going to use that sum function and add up all those coefficients multiplied by the hypothetical X value for this person. Or I should say the X values for the hypothetical person. That's how I should say it. Okay. So this person's predicted GPA will be 3.26. So what you can do, sorry, first of all, before I keep going, are there any questions on that? Or keep moving here. So this is how we would use regression output to make predictions, right? Once we have those coefficients, You're just plugging in the hypothetical person's X values and you can come up with what their predicted GPA would be. Yeah.
Could you say again which one was the intercept?
Yep. So if you go up to this very first row, right, we've got the coefficient on the intercept. The way that I just wanted to be able to drag this down, like I could leave this off, add these all up, and then just remember, I also have to add in that coefficient. Where was it? For the intercept. But I think that probably an easier way to see, I get the same value. I think the easier way to set it up is just put a 1 in there. That way it's like, just multiply the intercept by 1, and that makes sure that you're just kind of always adding it in. So multiply that coefficient by 1. That way we're making sure it always gets added in when we just take the sum of all these. Does that make sense? Yeah. That's a good question. Any other questions? We'll keep moving here. Okay, so one thing I could do, or could be asked, is if I look through these variables and say, which of these are, or which of these have a significant relationship with GPA, right, at the 10% significance level. So what I'm saying there is, when I look at these coefficients, I always start out with the same null hypothesis for every coefficient, which is that whatever that slope is, right? Maybe it's, the slope on the third variable, the slope on the fifth variable, whatever it is, we always assume that the relationship doesn't exist, right? That there is not a significant relationship between that X variable and our Y variable. If we can find a p-value that's less than alpha, we can reject the null, which means we're rejecting that there's no relationship. Or said differently, we're suggesting that we found evidence that there is a relationship. So what we would say, like at the 10% significance level, where alpha is 0.1, we would then say for every variable that has a p-value, for every coefficient estimate that has a p-value less than 0.1, we would say there is a significant relationship, or we can reject that there's not a significant relationship. So we'll go through our variables. I'll kind of show you a kind of a neat way to do this. I'm just going to insert a column here. So we can use something that I showed you a little bit with hypothesis testing, but we can use this if statement. So what I can do is actually make a rejection decision pretty quickly without like having to look at these and maybe make a mistake. And I'll show you how you can maybe make a mistake here in a second. And just say, look, if this coefficient estimate, if it has a p-value that's less than, and actually, I'm going to actually use this cell right here. I'm just going to put my alpha value up there. That way, if I wanted to, I could change it. Okay? So if it's less than, well, let's do that first so it makes a little more sense, right? So let's say I put my alpha value up there. And then I say if the p-value on this coefficient estimate is less than that alpha value, comma, put the word reject, if that's true, comma, if it's not, just put the word fail, right? Or fail to reject if I really wanted to make this a little lengthier, okay? So once again, that if statement makes life a little bit easier because now when I drag this down, although if I drag this down, what do I have to make sure I do? Yeah, I want the p-value to keep updating to the next coefficient, but I'm always using the same alpha value to check against or the same kind of significance level. So I'm going to freeze that cell reference, okay? Now when I drag this down or double, sorry, I could drag it down, or if I get this black plus sign, if I double left click, it fills it down to the very last point of data. So either way, I quickly get my rejection decisions, right? So everywhere where I see a reject, I'm actually saying that there is a significant relationship, right? Because I'm rejecting that there's no relationship. So if I wanted to even make sure that I don't forget that, I could say that significant or not significant. Oop, if this isn't true. Okay. Maybe that way it's a little bit easier. So I copy this down, maybe all the way though. So it looks like everything except for that verbal math test and the indicator on whether or not the individual is white, right? Everything else I would say has a significant predictive power about GPA, or it has a significant relationship with GPA. Now I could do this by hand, like so when it comes to that final Excel homework that's up there, I can ask you to do a similar thing. You can go through and just tell me, I can reject these variables because the p-value is less than whatever the alpha is. But if I'm looking through this, a lot of times I see this mistake. I mean, a lot. You look at this and say, well, the only ones that are significant would be the black indicator variable, and that's it. Well, no, all these e to the negatives means move the decimal point that many places to the left. So anywhere where you see an e to the negative, those are all significant as well, because those p-values are basically 0. Okay. Any other questions other than that? Or sorry, other than that, on that. So you can go through and do it by hand, but here, right, Excel is kind of treating these as really, really small values. It doesn't make the mistake just looking at it, right? And we should even remember p-values, right, should be somewhere between 0 and 1. So if I see a 5 e to the negative 18, there's no way my p-value can be 5. It must be that I have to move the decimal point a certain number of places. Okay. So we would say that, all of these, the vast majority of these variables that we included have a significant relationship with the exception of 2. Now, when we're making our predictions, even though those aren't significant, right, we still use them in making our predictions. Right? It's still that they're valuable estimates. It's just that we can't say at a certain level that they're statistically or significant, or they're statistically any different from 0, right? Maybe we could if we got a higher sample size, right? I think we talked about maybe a little bit last class. I might be mixing up my classes here, but when we're calculating the test statistic for all these coefficients, it's just take that coefficient estimate and divide it by something called the standard error. Well, that standard error is very similar to what we were doing before when we had sample means and assumed true means. I just remember here, our assumed true coefficient value was always 0. What we divided by was the standard deviation of our sample means before. So the standard error, if you want to think about it, it's kind of like the standard deviation on those sample coefficients. Remember, these coefficient estimates we get from Excel are still coming from sample data, okay? So that's kind of what we're doing. And just like the standard deviation of sample means, this standard error, what was it? Take my y, predicted y's, subtract. I can't actually write this out for you. So it's like you hold the other things constant. Don't worry about this for right now. But all we need to know is that there's a sample size in the denominator, right? And so that if I increase that sample size, right, it's going to decrease that standard deviation, increasing my test statistic, decreasing my p-value. So having higher sample sizes, even if I see the same coefficient estimate, it's going to drive down my standard errors and kind of increase my test statistic and then decrease my p-value. Now, I won't make you kind of walk through that line of logic, but it is another added benefit. Once again, I mentioned as many things in here as I can, where it's just greater to have a larger sample size, right? Any questions up to this point? Okay, so I think I have, what do I want to do here? We'll go back here. I think that's all I want to do with this GPA data. So if we go to the slides that I put up for this week, and actually let me make sure that these are the same slides. I don't think that they, oops, I don't want that either. I want this. So let's go to make sure that we're working with the same thing. So the ones that I uploaded should be called more regression. Let me see. 28, yes, this is from my other class. All right. So we went through a lot of this last class. You guys are a little bit ahead, so that'll help you out. We kind of talked about correlation, causation. We started thinking about it primarily with this student athlete variable and adding in the SAT as well as other variables, right? So one thing that we can do, and I think instead of using the slides, I have an example that I think is interesting. So we go back, I showed you this slide where I said, look, if you run a linear regression where you leave out an important variable x2, what the estimate that you will see from the data includes the true relationship, but also this bias component. Now, I won't expect you to understand, or I won't expect you to do this or ask you a question on the exam like this, but I do want to show you because I think it's interesting. Moving on from this class, you would start to really want to be able to think about what this bias component is, and then think about why, when some people show you some results, maybe you could actually put a sign to that bias. So notice, and I'll rewrite this because I think it helps. So when I come up with that slope coefficient estimate, it's going to include the true relationship between that x1 and y variable. It's also going to include this additional component, which is whatever the relationship is between y and this x2 variable that you left out of your regression. So what would the effect be if you put that x2 variable in, multiplied by the covariance between x1 and x2, divided by the variance, and this is what I always forget, I think it's the variance of x1, or is it the variance of x2? Yeah, variance of x1. So we can't really put a value to what that bias is. We don't know how large or how small it'll be, but we can usually sign it because the variance of a variable is always positive. Okay. So there, if we can think about, okay, I left out this important other variable x2, what's its relationship with the variable that I did include? I could put a sign on that covariance. And then what do I think the relationship would be between that x2 variable and my y variable? And I could put a sign on the coefficient or the relationship between that variable I left out and my y variable. So I can put a sign to what that bias would be. So I'm going to kind of walk through an example and show you how we would do this. So I think I put it up there, but let's just double check. We go to in-class data. You should have this COVID regression data. So I'm going to open it up from here. Okay, put it, yeah, here it is. So we got this COVID regression data. So I had a bunch of this COVID data. I thought it may be interesting to start playing around with it, showing you some stuff with it already. I put in some new variables and things that are a little more usable for this linear regression to give us some actual interesting results. So maybe I go to my regression tool, and the initial thing I think about is, can I predict cases per person in these counties? So this is like the number of new cases. I think it was from June to October this year, divided by the population, right? So kind of accounting for that. So I select that column. My y variable, I'm going to say, can I explain that with the percent vaccinated, not unvaccinated. So I select that. I hit OK, and I get my regression output, right? So we'll blow this up here. So it looks like, how would I interpret this? Well, this percent vaccinated, the units is percents, right? It just kind of measures the percentage. So for every 1% of the population that gets vaccinated, or in a county that gets vaccinated, you would expect the cases per, and I believe I had it in thousands of people. We'll check in a second. The number of cases per 1,000 people goes down by 0.25 people. Now, it sounds small, but I mean, in some of these counties, right, we've got millions of people. So, you know, if that's how many people out of 1,000, you know, scale that up to however large the county is, and that's how many, the number of additional people that you would see getting COVID. It's also highly significant, right? Its p-value is basically 0, so we could say that it has a significant relationship at every single level, right? Its p-value will be less than alpha of 0.1, 0.05, and 0.01. So we reject the null at every level, right? Or we reject that there's not a significant relationship, that we found evidence there is a significant relationship at every level. Okay. So what we just picked up, what we observe is that coefficient estimate. Okay, so I think I said it was negative 0.25. Okay. Well, that's going to capture this true effect. I don't know what that is. You know, I can't observe that. But it's also going to have this bias component if I leave out another important x2 variable. So I think I might have mentioned this. I showed you some of this data before. But, you know, we're not capturing, you know, what counties are more likely to have people get vaccinated or unvaccinated. Probably depends something on like the socioeconomic measures in that area. So I'm going to use one because I think we can actually come up with a pretty consistent story. I don't think you would necessarily push it back against this. And this is all like ahead of time, right? So this is not, post hoc. We're not looking at this like hindsight's 2020. We're trying to think about, okay, if I left this variable out, usually the reason we left it out is because we don't have data on it. I've got an income measure in that data set. We can definitely include it, and it lets us see what this bias would be. But in practice, it would be something like, okay, I don't have income data for these counties. So how might my coefficient be biased, right? Well, if you had to guess, right, and we're thinking about our X1 variable is the percent vaccinated, what do you think is probably true about the covariance between the percent vaccinated in a county and the average income? So as people have more money, do you think that it's more or less likely that they get vaccinated? Well, if we just think about healthcare in general, generally more income means everyone's you're more invest in your health. You might take different measures, and maybe it's just an education thing as well. Like maybe those lower incomes is picking up. There's less education on vaccines, so you're more likely to be kind of wary of them, right? It's not necessarily good or a bad thing. It's just kind of what we would expect. So higher incomes are likely correlated with higher percent getting vaccinated in the county. So you expect this covariance is probably positive, at least based off of, you could look at flu vaccines or all these other vaccines, and that's generally the case, right? You look at who's getting flu vaccines, it's usually, the income tends to be on average higher. Obviously, it doesn't fit for every person. We're talking about kind of the average relationship. And if we think about income, right, and kind of the number of new cases, what might also be true? Well, first of all, if you have more income, you had the luxury, you weren't as concerned during a quarantine, right? If you're in a lower income, level, like I need to work, right? I need to pay my bills. And so if we look at the relationship between income and the number of new cases, well, a lot of those lower income level counties, the people can't stop, going on about their everyday activities. And so you might think that the relationship between income and your Y variable, which was the number of new cases, maybe that was maybe that was negative. If people have more money, they were less likely to have to go out, they could kind of take more precautionary measures. And so the number of new cases potentially in those higher income counties was lower. Okay. Now, this is all not based off the data. This is based off intuition initially, right? But we could check this if we actually had the data, which we do here, right? So I had this medium household income by every county. So first of all, let's just look at the covariance between X1 and X2, or actually, let's just give them names: the percent vaccinated and income, right? Scroll over here. We'll zoom in a little bit so we can see this better. All right, so I just typed in here, I want to look at the covariance. So just going back a ways, but we have a covariance equation. I'm going to use the sample one. So I'm going to use my X variable would be percent vaccinated, comma, scroll back up. The second variable was income. So select that, hit enter. Maybe hit enter. There we go. And I get a positive covariance. So that kind of lines up with our thinking. Then I could actually, if I really wanted to, what would that coefficient be, B2, if I include it in the regression? Well, I can't necessarily observe that until I actually include it in the regression. So now we're going to run a regression where our Y variable is still the cases per person, but our X variables would be household income and percent vaccinated. So I'm going to hold control and try to select both of these. The problem is, excuse me, that if I try to select both, okay, I've got them both selected now. If I hit OK, Excel's mad. So this contiguous reference, what that means is whenever you include multiple X variables on the right-hand side, in Excel, they need to be next to each other. In other computer programs that can like pick up and move things behind the scenes for you, Excel doesn't have that capability. It's not as strong of a statistical it doesn't have as strong of statistical analysis, but it's easy enough to insert a column, move income over to be next to that percent vaccinated, move everything over so we don't have a blank column. And now when I go to run that regression and I want to select my X variables, Now they're right next to each other. Now it can include both of them at the same time, okay? So a little bit of an annoying thing about doing regression in Excel is, you have to make sure that those variables are right next to each other, okay? Any questions over anything done here in the last little bit before we kind of dive into this? All right, so we had a sign on that covariance that was positive, which kind of lined up with our thinking. If we see a coefficient on that second variable that's negative, what would the sign of our bias be? Well, I've got a negative times a positive divided by a positive. So what that's really saying is this additional component that I'm adding in is a negative value. So the coefficient I was seeing before is going to have the true effect plus some additional negative component. Maybe this is actually closer to 0, right? Maybe the new estimate I get, because once I include this second variable of income in the regression, this entire bias component goes away. So as soon as I include it in the regression, Excel, like what we're doing behind the scenes, we're able to hold it constant. Remember, the interpretation of our coefficients with this multiple linear regression was the same exact thing. 1 unit increase causes this, predicted change of y, holding everything else in the regression constant. Okay. So now when I ran that regression where I had both variables in there, notice the household income one is negative, right? So our intuition was correct about that relationship between our second variable of income and our y variable, right? It does end up being negative. Okay? And it looks small, but right, what we're saying here, how would we interpret this? Well, the units of household income was literally it was representing the dollar amount. So a $1 increase in median household income in a county decreases the number of new cases per, I think it was 1,000 people by 0.0003. Well, yeah, if you only have one more, dollar average income, it's not going to be a large effect. You probably want to do something like here. Okay, well, what's the effect if it's $5,000 higher in a county? Because that's a sizable difference, right? And so maybe if I go from a county that has a lower income and then a county that has additional $5,000 of average median income, so it take that 5,000, multiply it by the effect of $1, and okay, now I'm decreasing it by about almost 2 people, right, per 1,000. Right? So, we can scale these effects up so that they have a little bit more usefulness. Okay? Now notice once I included that second variable of income, my bias component goes away, right? So now it's more likely I'm picking up this accurate kind of relationship between X1 and Y. So now it looks like the percent vaccinated, if it goes up by 1%, it only decreases the number by about 0.13 per 1,000 people, number of new cases. Any questions on that? Does it make sense there? Like I said, I won't expect you to know how to, or like to put a sign on that bias, but I do expect you to know that it exists if we omit one of these important variables. I think I'll keep using this data set. I think I had one more thing that I thought was a good teaching tool. So let's go to data analysis, regression, same y variable, but now for my x variables, I'm going to include a bunch of stuff over here. Right? So I'm going to include from Midwest over to the percent unvaccinated. And the reason why I didn't include, well, I'll show you actually. I'll show you why I didn't include all of these. So here were indicator variables for what region the state was classified, the county was in. So the way that the government, you can look up these maps online. And it's used for a lot of things like with the census, but you've got the South, Midwest, Northeast, West, and the Pacific. I think the Pacific includes like Alaska and Hawaii. Right? So I've got these other variables, which are 1 or 0 if it was a metro county, right? Kind of capturing that, big cities might be a little bit different in terms of the spread of COVID in smaller areas. The unemployment rate and the household income to kind of control for some of these socioeconomic factors. And then region of the country, that should hopefully capture some things like temperature that could alter behavior. Now, if I select all of these and run this regression, actually, why is it mad at me? So let me see. Let me try this one more time. One of these variables might have an error in it that I didn't save. It does. So which one is it? I think, well, it can't be income. We've already used that. think there might be a missing, yeah. So this is another good kind of thing to show. So you can't run a regression if your variable has blanks. I think when I was uploading this data, some of these I could was like merging stuff, and some of them just only exist in one. And now I remember the issue. It's these Alaska counties because nobody lives there, right? So I thought I deleted these before I posted it. I forgot. So you'd have to go delete these. We can't use them. They have, blank observations. So then go back to this filter tool, select all. So now I can see all of my data again, right? So now I'll show you what happens if you try to include all of those regions. So we're going to select cases per person. We're going to select from % vaccinated all the way over to South. Now, when I hit OK, notice I get something weird here. Right? What's going on? Well, because if you're a state, you have to be classified in one of these regions. The coefficient's like, what am I comparing to? If I included all of them, it'd be the expected change in the number of new cases from being in the South relative to what? So you have to leave out one of those categories. Now, I won't give you examples where you have to know that you should leave out a certain category. If I ever gave you something like this, I would either just give you the results directly and kind of mention which group was left out. So I didn't know that ahead of time. So now what I'm going to do is leave out the South here. Okay. So, oops, I did not mean to do that. I need to reselect it. So regression, okay. Select my X variables, Midwest to % vaccinated. So I'm leaving out the South. So now when I run this, okay, now everything has a coefficient. Things are looking a little bit more like they were before. Okay. So now if I'm looking at this output, right, I'm controlling for a lot more factors. So basically what I'm able to do is say, look, if I had two counties that are in the same region, right, they're in whatever region it is, they're in the same one. They're both either metro or non-metro counties. They both have the same unemployment rate. They both have the same median household income, but one of them has 1% more of their population vaccinated, then we would expect the number of new cases that they see to go up by 0.04. So this seems like counterintuitive, right? Because there's a higher percent of the population vaccinated, but we're seeing that effect, once I'm starting to control for some of these other factors, is positive. Well, there's two things that could be going on. So the first one I'll mention is something that we've already looked at. So in practice, when we run these regressions, I was, gave you an example where I was treating it as though income was the only other important omitted variable that we had. What we're actually picking up, is the true effect, right, of the % vaccinated. But here's this bias component. But there's also possibly other variables as well, right? And I could, keep writing this out for however many other important omitted variables there are. So it's very hard to ever completely eliminate these omitted variable biases unless you have a lot of additional variables and such that once you include them, you're getting R squareds close to 98, 99, because then well, even if I left something out, it's not very predictive. Whatever's left out, I mean, I've only got 1% of the variation I can't explain, so it's not going to have near as large of an impact. But our R-squared was what, around 30%? So there's still a bunch of these variables that we left out, including income, eliminated this bias, but maybe we still have this one, right? So maybe it's that the percent vaccinated in the county is still correlated with other things that are important that we're leaving out of the equation. Now, I would argue we've captured, some good ones like location, socioeconomic, kind of urban versus rural. We've tried to capture some of these things we think are probably really important, but maybe we left some things out. It also could be, and this is one where it's very difficult. We have to always remember these are just correlations. So let's say we see the percent of a county vaccinated go up. What do you think people might tend to do when they're vaccinated? Yeah, right. It alters behaviors. So we're never going to be able to pick. Oh, I shouldn't say never. With the way that we can track phones and stuff, I'm sure some company out there has data where they could somehow do some geospatial stuff and figure out what were people's behaviors before and after, right? They got vaccinated before and after a large percent of the county got vaccinated. But that could be part of the story as well, right? Is that it's causing this other thing to change, right? That we are able to observe, which is then causing the cases to go up. So it's not that just getting vaccinated, right, or percent of your county vaccinated higher is going to lead to more cases. If you can get the percent of your county vaccinated and then curtail these behaviors that you think might be increasing after a larger percent of the population is vaccinated, then maybe you could actually see there's a pretty strong kind of negative effect. But hey, it's hard to pick up. This kind of highlights that like this is not an easy thing. These are just correlations, which is why like the next level of statistics is you're moving from how can I pick up these relationships to how can I pick up these relationships, but make sure I can say they're causal, right? So, certain ways that you would do this is something like, you would look at, the percent vaccinated, but maybe you also compare states that have different mandates before and after the mandates. So you can pick up like, we call it difference in differences. There's all these really cool techniques that you can really actually pick up causal relationships. All these things that I just mentioned, we can actually eliminate those, but we don't have enough time. So, we won't get to that. So, any questions for me? Otherwise, I'll end a little bit early here today. So I think on Wednesday, I'll keep going through more examples. One thing I'm going to do, since you're all here, we've got a little bit extra time on your way out. I'm going to pick up, everybody's going to get, if I can get out of all the junk I have open, everybody will get 10 out of 10 for the day. This will be the last day I use iClickers. I'm going to put together, go through, drop your lowest score, or your lowest 3 scores, sorry, and then put up what your grade with those scores dropped is on Canvas at some point during this week. It's on my agenda. I would say I'll get to it tomorrow, but I'm not 100% sure. But that'll get up there on Canvas. And then Wednesday, I'll bring this file in. And obviously, we still have those 2 Connect and Excels that are out there. Once those are turned in, I'll kind of move those to be factored into your grade. Once I get those Excels graded, I'll move that. And I'll give you this figure out your grade tool. So I'll show you how to use it Wednesday. I'll get it up there on Canvas. You should have your final iClicker score by, like I said, hopefully by Wednesday, if not Friday for sure. And you can start to play around with, okay, if I get this on the final or I get that, it'll kind of change the weights for you so you can see what your final grade would be.
Have you posted the video on YouTube for this Excel assignment?
So it would be from what we did last class, which that should be up there. And then what we did today would be helpful as well.
Are you gonna have one video where it's
I'll try to splice one together this afternoon and get it up there. If my video editing software was acting weird before, so hopefully I don't have to do it in like 2 parts, but I think I can get something spliced together. I think I got it updated. So everybody on the way out, make sure you answer any letter for the iClicker, get the 10 out of 10 for the day, last time, and we will see you guys on Wednesday.
I was gonna ask because I was emailing you and I thought you said you needed 4 connected or 5 connected boards. So
it's always 1 less. So we've got what, 6 connect? So I think at the beginning of the semester, I mentioned usually we have like 5 assignments, but for up to this point, so there's 6
because I only have 4 in the grade book right now. Because this is gonna be connect number 5. Unless I'm wrong, and then this is gonna be connect 5 and Excel 4. That's what I was.
So I've got connect 5 and 6 and Excel 4 and 5.
Oh, so this isn't the last one. There's another.
The one that's due Wednesday?
Yeah.
Yeah, so that's not the last one.
Oh.
So that's why I said these last 2 that I'm putting up were like, if it's not as much time as we've had in some of the other assignments.
Yeah.
But that's because if up to this point you've done the first 4 Excel and you've done the first 5 Connect, then those last 2 would just be your lowest and they get dropped.
Okay.
But if you want to kind of do that, and to be honest, like the Excel 5 is probably a little bit, it's the regression, it's a little bit easier, probably takes a little bit less time.
Yeah.
So, you kind of almost like pick and choose if you've done all the assignments up to this point, which Excel you want to do and which Connect you want to do.
Okay.
Does that make sense?
Yeah.
Okay. Yeah.
Okay, so I couldn't remember, did you